Here we are at lesson 3 for chapter 10 on solids. So we're still going to relate to the kinetic molecular theory. So I hope you guys are paying attention to what that means. Let me pull up the slides. Let me go back to the beginning. All right, so in section 3 with the solids, I didn't do that right. So sorry. So we'll pick up here. Here we go. All right, so solids. Solid particles compared to liquids and gases are the most closely packed together. And because they're so closely packed, the attractive forces are stronger, but they still do have motion. Okay, they can vibrate about a fixed point. So it's not that they're just like totally still. They do still have some energy. And so they're able to sit in a fixed position, but they vibrate around a fixed point. Okay, so they don't move nearly as much, of course, as liquids or gases. We divide solids into 2 categories. They are either crystalline or amorphous. So crystalline solids have a crystal structure to them. They have this geometric pattern. And we'll look at that a little bit more here in a second, but they form these shapes. Amorphous do not form said shapes. They are very randomly arranged. And so that gives some different properties to them. Most of your solids are crystalline. Amorphic solids would include glass and plastics. And then we'll come back to both of them a little bit later, talk more about some of their specific properties as we kind of go through this. The general properties of solids, they tend to have definite shape and volume. Of course, they're solids. The particles aren't moving around. So gases have no definite shape and no definite volume, right? They just expand to fill whatever container they're in. Liquids have a definite volume, but they take on the shape of whatever container. But solids tend to stay the same shape. The exception to that is when you change their temperature, they can expand or contract a little bit. So I have a video here that we'll watch. I don't remember if it has sound or not. Come on. So this is called the ring and ball experiment. So the ball fits through a little apparatus here when it's at room temperature, so before we heat it. But then once you heat up the ball, which we'll get to in a second, okay, so they just stick it in the flame for about 5 minutes. We'll let it get nice and warm, let those particles gain some energy. And as they gain energy, they do spread out just a little. So it gets stuck. It stucks, I don't know. So it gets stuck until it cools off. And then as it cools, it returns to that original volume. And so it does slide through. And so that's solids for you. So you can change their volume just a little bit by changing the temperature, but it's usually not a very drastic change. This is why, especially in areas that have real winter, when you get to a bridge, you'll see like a metal strip that goes across that has 2 parts to it, like teeth that are I can't think of the word, but they're stuck together. Those are expansion joints, so that as winter comes on and the bridge gets really cold, they can expand a little bit and keep the road all together. Otherwise, the bridges would be breaking all the time. Okay, so it allows for, as the concrete contracts because it's cold, those expansion joints prevent the concrete in the bridge from breaking apart from the concrete of the rest of the road. So it's another example of how that kind of comes into play. Solids, at least crystalline solids, have a definite melting point. When we get to a particular temperature, the solid starts to melt to a liquid. Amorphous solids tend to melt over a range. We'll kind of come back to that a little bit as we get into lesson 4, where we're talking about changes of state. So amorphous solids, because they don't always melt at a specific point, they melt over this range and they kind of just flow. They're called, or they're sometimes considered supercooled liquids. So they have these kind of liquidy properties, even at temperatures when they appear to be solid. So that's what a supercooled liquid is. Solids have the highest density of the 3 types of, or the 3 states of matter. You have the molecules are the most compact in a solid, generally. Water is one exception. I'm not going to say it's the only exception because there might be something else, but it's one exception where the solid form is actually less dense than the liquid form. But solids are incompressible. So once you have something compressed down to a solid state, there's really no space between the particles. You can't compress them anymore. There are some things that we think of as being solids but compressible, but they're really not, like cork or wood or something. What you're doing is squeezing the air out, but you're not actually compressing the solid material. And then solids have a very low rate of diffusion, so you can have diffusion of the particles within a solid, but it's very, very slow. It takes a very long time. So for instance, if you put a zinc plate and a copper plate and clamp them together for a very long time, you would eventually find a few atoms of each of the metals in the other one. But it's a very slow process, like millions of times slower in a solid than it would be in a liquid or a gas. Okay, so there's a very low rate of diffusion. Diffusion occurs very slowly. All right, let's come back to this idea of crystal structure. So the crystal structure is the 3D arrangement of the particles. And we can describe either the lattice or the unit cell. So the lattice is the like a coordinate system that's showing where all the particles are at. I don't have a picture of this, but your book kind of does. And then the smallest portion of that lattice that still maintains the overall shape is called the unit cell. Okay, and other than knowing those definitions, I'm not really going to ask you to apply that. There are 7 shapes of crystals. You don't have to be able to like look at a sample and tell me what it is. I don't care. Just knowing that there are different shapes, we're good. Okay, so you don't have to be able to give examples. You don't have to be able to identify those shapes. Just know that there are 7 shapes. There are multiple shapes to these crystals. So there's 7 shapes of crystals, but 4 types. And these you might need to know a little bit more of. So we're going to discuss each of these. They kind of, they have their own properties. So depending on which type of crystal you have, that determines the specific properties of that substance. Okay, so for instance, ionic crystals. So these are going to be substances that, think back to last semester, we talked about ionic compounds. They're going to be made up of positive and negative ions, okay, like table salt. Okay. So you have this very regular pattern of the ions that are alternating around. They form substances, they're solid, in their solid state, they're going to be hard and brittle. So it's being a hard substance, but it will break apart. They have high melting points and they make good insulators. The covalent network crystals form when you have covalent bonds between the atoms. So like diamond is a covalent network crystal. Again, hard and brittle, very high melting points. They're generally non-conductors, or some of them are are semiconductors. The metallic crystals, these are going to have metallic bonds, right? So you have that metal, the positive metal nucleus that's surrounded by the sea of electrons, right? They just kind of share their valence electrons around within the sample. So they're very conductive. So metallic would be any of the metals. When you have just a sample of the metal, like mercury or iron or copper, okay? And then the last type are the covalent molecular crystals, where you have what we call intermolecular forces that are holding these things together. So we haven't talked a whole lot about intermolecular forces. These are things like hydrogen bonding, or we have what's called dispersion forces, London dispersion forces. So they're weaker attractions between molecules holding them together. Because they have these weaker attractions holding the particles together, they're going to vaporize more easily. They're going to melt more easily. So they melt and boil at lower points. They tend to be soft, and they do tend to make good insulators. Okay. I think this is a typo. I think that's supposed to say good conductors. Your book says insulators. I think that's supposed to be conductors. Because ionic substances, oh, not in their solid state. That's ionic substances do not conduct electricity in their solid state. Okay, so they are good insulators. Remember, it's just when you dissolve them in water, or if you melt them, and then those ions are no longer bound together, you have that flow of charges, and then they will conduct electricity. Okay. All right, so that's the end. We're not doing a lab with solids because there's not a whole lot to do, but we will do a lab after the next lesson. All right, so again, message me with questions. But other than that, good luck on homework. And so